In this video, we're continuing our discussion of multiple degree of freedom systems. Here we're going to discuss influence coefficients. So to date, we have used Newton's laws to get the equations of motion for multiple degree of freedom systems. We could also obtain them using influence coefficients, which are based on Newton's laws but can be easier to apply. So these influence coefficients relate the effects of forces and displacements from one part of a system to another. There is one set of influence coefficients that can be associated with each matrix in the equations of motion. If the coordinate system is changed, the influence coefficients will also be changed, so they're dependent on the coordinate system that we choose in the beginning. So for the stiffness matrix, we can use one of two related sets of influence coefficients. We can use stiffness influence coefficients, or we can use flexibility influence coefficients. For the mass matrix, we can use inertia influence coefficients. So flexibility influence coefficients are denoted Aij, and they're defined as the deflection of coordinate I in the positive direction due to the application of a unit load at coordinate j in the positive direction when all other coordinates are fixed. So this is similar to the flexibility approach to find equivalent stiffness for a single degree of freedom system and is a statics problem. And for a torsional system, Aij is the rotation of coordinate I due to a unit torque applied at j with all other coordinates fixed. Stiffness influence coefficients, Kij, are defined as the force required at coordinate I in the positive direction to maintain a unit deflection at coordinate j in the positive direction when all other coordinates are fixed. So this is similar to the stiffness approach to find equivalent stiffness for a single degree of freedom system and is, again, a statics problem. For a torsional system, Kij is the torque required at coordinate I to maintain a unit rotation applied at j with all other coordinates fixed. Now, inertia influence coefficients, Mij, are defined as the impulse that must be applied at coordinate I in the positive direction to produce a unit velocity at coordinate j in the positive direction while maintaining zero velocity for all other coordinates. Alternatively, Mij can be defined as the force that must be applied at coordinate I in the positive direction to produce a unit acceleration at coordinate j in the positive direction while maintaining zero acceleration for all other coordinates. Now we can discuss some properties of stiffness and flexibility influence coefficients. So the total force Fi acting on the ith coordinate direction can be found from the sum of all displacements xj, where j is equal from 1 to up to n in the system. So Fi is the sum, j goes from 1 to n, of Kij xj. Or, in matrix form, F is equal to Kx, where F is the column vector of the forces acting on the system in the positive direction, and K is the matrix of stiffness influence coefficients. So if a coordinate had an angular displacement, F would have units of torque for the corresponding coordinate. Similarly, the total displacement in the ith coordinate direction can be found from all the forces Fj, where j goes from 1 to n, for the system. So Xi is equal to the sum, as j goes from 1 to n, of Aij Fj. Or in matrix form, X is equal to AF, where A is the matrix of flexibility influence coefficients. And again, we note that if a coordinate is an angular displacement, then the corresponding term in X would be a rotation. Now, if we substitute 8.33 into 8.32, we get F is equal to Kx, which is equal to K times AF, which is equal to Ka times F. And starting with the other direction, we have X is equal to AF, which is equal to A times Kx, or AK times X. So this shows that Ka is equal to Ak, which is equal to the identity matrix. So this implies that K is equal to the inverse of A, and A is equal to the inverse of K. So what we've shown is that the matrices of stiffness and flexibility influence coefficients are inverses of one another. And it can also be shown that the matrices of stiffness and flexibility influence coefficients are symmetric.